How are you folks? The snowstorm was pretty brutal yesterday. I had to take my car out and I spent 30 minutes just shoving the snow away. Kind of annoying. Okay, I guess let's get started. Uh, so, in the previous lectures, we have seen processes and then process synchronization, various aspects related to process concurrency, locks, semaphores, so on and so forth. So, in this week, we'll be looking into CPU scheduling. So yeah, before understanding what CPU scheduling is, what are the different scheduling policy, what is CPU scheduling? So it's basically the process of switching CPU from one process to the other process, right? So operating system has to do this. So this is what we call CPU scheduling. So we actually saw an example of CPU scheduling in lecture 3, where this is a non-preemptive scheduling. That means here we are not we will never snatch the CPU away from the process. Rather, process actually gives up the CPU. So here, as you can see, the scheduling decision or switching of the process only happens in three cases. One, when the process terminates. The second case, when the process gets blocked because it is waiting for some resource. And third case is when the process it actually yields the CPU. Like process can actually tell to the operating system that it has nothing more to do right now. So it can actually yield the CPU to operating system, at which operating system can now put the current process in sleep and schedule another process. Okay. So what's wrong with the non-preemptive scheduling that we saw, right? What's wrong with it? Like there are one problem is, imagine if there is a process that has been running that takes like 2 hours. Okay, if that process is running on the CPU, it actually can starve all the other processes that are in the system, right? Because all the other processes now has to wait for this long running process to complete. Okay? And this can lead to system being non-responsive. Imagine when you open Chrome, if the Chrome doesn't come up, right? So the system becomes non-responsive. Users won't like that. And also it's very inefficient use of other resources. For instance, since only one process can be running at any time, like imagine a long running process which is running for, let's say, 5 minutes, and the system has many resources apart from CPU, like network, IO devices, disks, so on and so forth. So if that process is not using any of these resources, then you can imagine that for the entire time the process is running, all these resources are not never used. However, there could be other processes that may want to use these resources. Since they are never scheduled, so all the other resources will be wasted. So we don't want this. So to avoid this, operating system designs have evolved over time. So right now we are in time sharing systems. So here each process gets switched so frequently that you almost get the feeling of interactive system. That means it's as if all the processes are running at the same time, because they'll be switching. Every process will make progress and they'll be switching continuously by the operating system. Okay. So this actually leads to a very responsive system, because none of the processes get stuck, because every process gets a chance within short window, right? And this is based on time slicing. Basically, we give each process certain fixed time, and when the time expires, like when the timer expires, we just schedule another process. And here, the scheduling decision happens in addition to all the regular scheduling. There is another scheduling that happens when the timer interrupt expires. That means when the timer expires, then then scheduler comes in and it will schedule another process. Okay. And the way operating system knows when the timer expired is through timer interrupts. So on usually hardware, like on your motherboard, there is a piece of hardware called clock, so which you can set to a predefined value. So when the clock expires, then you'll get an interrupt. So that is called timer interrupt. So, and when the timer interrupt occurs, then operating system knows that corresponding time has elapsed. That means it's time to switch the process. So basically, what happens is when a process runs, uh, operating system starts the timer and let a process run. And when the timer expires, then operating system will just do the scheduling. Okay. And in order to do scheduling, there are two things. We need to know how to do scheduling, and we need to know when to do scheduling. And we know from the previous, from our first lecture, that how is a mechanism and when is a policy, right? And we also know that we should separate policy from mechanism. Okay, so that this leads to flexibilities, because mechanism is usually fixed. How to do something is given, right? But when to do something is actually a different aspect, and that might need more modifications rather than how to do something, right? Because most of the times there is a fixed way you have to do, you can do something. But when to do something is a decision that user may wants to configure, or operating system may need to change it, so
¿Tienes
on
que ir
and
ya?
so forth.
Bueno,
Go on. uh, Guys,
y
are you
después
here?
vuelves a subir. Gracias por quedarte conmigo.
Hey, can I think one of you guys have their mic on. Can you please mute your mic, please? Okay, thank you. So let's see how to do the switching. So how we know, right? So this is the context switch. So when we have to switch between two processes, we just save the state of the current process into the PCB, and then we take the process that we want to schedule, and we reload the state from PCB, process control block, and then the other process starts executing. So this is the mechanism. We know how to do it. So when to do it? This is when things become really tricky. There is no single answer. We can never, there is no single policy or like single way in which it can be done efficiently, because there could be conflicting goals. For instance, depending on how we want our operating system to behave, this policy or the scheduling decisions could vary. For instance, if we want our operating system to be fair, then we may have to compromise on efficiency. Similarly, if we want our operating system to be efficient, then we may have to compromise on portability, because then operating system is no more like configurable. So this policy decision usually varies with the requirements. I mean, it depends on the use case of the operating system. It depends on what we want from the operating system. Okay, so there is no single answer, and it depends on the use case that we want, that we are interested in. And so, what are the challenges in making a good policy, right? like why is it hard to make a good policy? Because there are different job types. For instance, there could be a program like a long running program versus short running programs. There could be programs that need more interaction with humans. There could be programs that don't need interactions, like for instance, uh, like model training. In case of machine learning, a process when you start training, it doesn't need interaction, it just runs for a long time, it doesn't need interaction. Similarly, there could be processes that are IO bound versus processes that need more CPU. An example of IO bound process is MySQL server. So an SQL server actually may need to access disk more often because that's where the database is stored. Whereas a machine learning algorithm, it just needs CPU because it needs to do a lot of matrix multiplications, right? So there are different kinds of jobs present in the operating system. So a good policy should actually take care of, should keep in mind that the requirements of different jobs are different, and not all the jobs have the same requirement. And also, a policy should also keep in mind of being fair, in the sense it should make sure that all the processes get some CPU time, and processes don't get starved, right? Like if there is a small, like a short term process or a process that takes small time, it should not wait for some process that takes longer time. Because why should some process wait for the other process, right? uh, so the policy should keep in mind, like, should make should make decisions which are fair. And another, like, one of the major challenges in policy is we cannot predict the future. That means, so operating system is dynamic in the sense the processes comes and goes. So we don't know, we cannot predict, like, long running process will come at time t1 in future, correct? So we don't know what are the process requirements that will come in future. So this makes like policy decisions hard. Like, so given this, we you can never say that one policy is good, because you never know what are the requirements in future. So let's say I'm using an operating system, let's say for my research. Let's say tomorrow I may use my operating system to host a web server. Then the processes that I run changed, right? Previously I want my system to be interactive, now I want my system to be efficient. So, and there is no single policy that optimizes both. So it's tricky. So this makes like designing CPU scheduling policies very challenging task. So, and any scheduling policy should have at least should at least strive to achieve four important goals. Okay, it doesn't matter which policy we come up with, it should try to have all these four goals. Okay, the first goal is to minimize turnaround time. That means average time to complete a job or like any process should be minimal. Okay, so note that this is average time in the sense uh, it's average across all the processes that have been running. Okay, and the second goal is to maximize throughput. That means the number of jobs that get completed per second should be maximum, in the sense it should be, basically we should make use of CPU efficiently. We should never use CPU to do something that is not needed by a process. That is what throughput means. Okay, and we should have short response time. That means when a process gets ready, or when a process wants to start, then it should start immediately. So the delay between when a process arrives and when it is first run, that is the response time, that should be less. On average it should be very small. Okay? And finally, policy should be fair. It should ensure that there is no process that is starved. Note that these goals are actually, they actually conflict with each other. For instance, we will see that in order to have short response time, we may have to compromise on the throughput, because in order to have a short response time, sorry, so we need to have shorter timer, right? Because we need to swap in and swap out processes quickly. That's what makes the system responsive, whereas that actually affects throughput, because we'll be switching more often. So we'll be doing more switching than actually using the cpu to do useful work. So we might spend more time just switching rather than doing the actual work. So that could reduce the throughput. So these are like very like conflicting goals. So it, this actually makes things really hard, and this is also one of the reason why like designing operating system is not trivial, because most of the decisions that we make are just depends on the use case. Okay, so now that we know the bad news that there is no perfect scheduling policy, let's look at a few possible scheduling policies and see what are the pros and cons of each of these policy. So, so first policy will be looking at FIFO, first in first out policy, or first come first serve policy. So here, what happens? It's the policy that we saw in lecture 3, where when a process comes, we run it until completion, and we will only do scheduling when the process is either blocked or it terminated or it voluntarily releases the cpu. So this is very simple, and it has almost no overhead, because we only do the scheduling when it is absolutely necessary, right? And what's the disadvantage? I mean, of course, it's not responsive. Like a long running job might actually starve uh, other jobs, and also now the other jobs may have to wait long time to get to run for the first time. So the response time will be very large. And the other policy is round robin. So here it's the simplest policy that any time sharing system can have. So here, each process, there is a queue maintained by the operating system called ready queue, which contains list of processes that are ready to be run. And so operating system picks a process, it runs it, and when the timer expires, it takes the next process, it runs it for the corresponding same time, then so on and so forth. It just goes through each of the processes in a round robin fashion continuously. Okay, so here the tricky thing is what is the timer value that we should use. Okay, so like uh, what do you think happens like when we choose a large time slice versus small time slice? Anyone? Like what? Like let's say if I choose, okay, let me ask another like question in different format. We know that in order to be responsive, the time should be small, right? Like we should quickly switch the processes. Okay. What happens if I make time slice very very small? Okay, like let's say 2 nanoseconds or like 3 nanoseconds. Okay, why is that a bad idea?
because processes that aren't atomic would uh, not be finished, and there's a lot of overhead in switching.
Perfect. Exactly. So context switch is not free. So in order to switch, there is work that needs to be done by the operating system. That means it is consuming CPU cycles. So imagine if context switch takes 4 milliseconds, whereas the timer is just two, let's say 3 nanoseconds. So that means we are actually using the CPU just for context switching, but not doing any useful work. So we cannot make the uh, like timer very very small. So that's actually a very bad idea, because the throughput decreases because there is a lot of overhead. And furthermore, fairness is not always good because, again, it depends on the jobs that we have on the system. So, let me show an example of why fairness is not good. When can be the case when fairness is not good, right? So, let's say there are 10 jobs that are simultaneously submitted to the system, and there are 10 jobs that are ready to be run. Okay. And each job takes 100 seconds. Okay. And assume there is no overhead. Basically, there is no context switch overhead, right? Let's assume that. And how much time do we need to complete all the jobs? It's 100 into 10, 100,000 seconds. Okay. So we know that irrespective of which scheduling policy we use, last job always finishes at 1000th second, right? So what is the point of scheduling? Because we know that it doesn't matter now because whatever um, whatever scheduling that we use, last job will always end at like 1000 second. So let's see, like if we when we use FIFO, okay, like first in first out, we start with job one, okay, and we start at time zero, and actually that should be time one, but yeah, okay, it's fine. So we start at zero and we end at 100. We start at job two, we'll start at 100 when the job one ends, and it ends at 200, so on and so forth. Finally, job 10 ends at 1000. So average turnaround time, which is the completion time minus arrival time. Okay. So since we all the jobs arrived at the same time, so time zero, so the turnaround time will be equal to the completion time, right? So average turnaround time is just average of the end time. So it's 550 seconds in case of FIFO scheduling. In case of round robin, it's 995. In case of round robin, we know that each we are assuming timer to expire after 1 second. So job one will execute at second zero. Sorry, job zero will execute at second zero. Job one at one, job two at two, in a round robin fashion, and finally, after 10 seconds, job zeros again gets a chance for 1 second, so on and so forth. So if you see the average turnaround time, it's 995, which is actually quite more than our FIFO. Okay, looks like unfair policy was actually better, right? Actually, unfair policy average turnaround time seems to be better than uh, like the fair scheduling or like round robin scheduling. So this just shows an hint of why we cannot have a policy that's always good at all times. Okay, because if this is your system configuration, let's say all the jobs come at the same time, every job takes 100 seconds, then of course round robin policy is very bad. Okay, but let's take another job configuration. Imagine now there are 10 jobs. So job 1 to 9, they're the same, they take 100 seconds each, whereas job 10 takes 10 seconds. Okay, now which policy is better? If we use FIFO, like everything stays the same except for job 10 now ends at 9:10. Okay. So here average turnaround time is 541. It decreased a bit. But round robin, actually average turnaround time, it decreased relatively more. Like our total work that needs to be done dropped by 9%. Whereas this 9% drop resulted in only 2% turnaround drop for FIFO, whereas 17% turnaround drop for round robin. So this should give you a hint like, okay. So it looks like for different job configurations, round robin seems to be doing better. Now consider like extreme case where job one takes 100 seconds and job 2 to 10 takes 10 seconds each. So now which policy is better? So if you look at, like, if you do the math, FIFO average turnaround time will be 145, whereas round robin it will be only 105. So this shows that actually, depending on the configuration of the jobs, or like depending on the job characteristics, round robin or FIFO might be better. Like, right? There is no policy that is good in all the contexts. And in general, like if you have shorter jobs, then usually round robin is good because average turnaround time will be less. And then when we want the responsiveness, like when we want more responsiveness and we can compromise on throughput, then of course round robin is better, okay, compared to FIFO. So another, like a more smarter way than to do dumb first in first out is to uh, schedule shortest job first. So SJF or STCF. STCF stands for shortest time to completion first scheduling. So here, similar to FIFO, but instead of scheduling jobs in the order they arrives, what we do is we given the completion time of each job, we actually sort them in ascending order and run in terms of like increasing completion time. Like here, C, A, B, they arrived at different times, whereas the shortest time, we know that A is a small job that has the least time to complete. So we run A first, and then the next largest is B, and then finally we run C. Okay. So here, actually, if you see, the average turnaround time decreases quite a lot compared to FIFO.
Quick question.
Go on.
How does the computer know beforehand how long each process will take?
Exactly. That has to be specified by the user. That's a very good question. Exactly. So that is one of the disadvantages of a shortest job first. Yeah. Computer will operating system may not always know, right? Yeah. The expectation is the user, when when she writes the program, she specifies the time that the program takes. Okay, that could give a hint. Okay,
Thank you.
but this is not possible in reality, right? As you can imagine.
Yeah.
So yeah, again, like shortest job first, although looks very good, actually you can prove that shortest job first always has the least turnaround time. Okay. However, it has obvious disadvantage. One, we need to know the runtime, like runtime for each process, which is hard, and we don't know the future, right? Because shortest job first works better when all the jobs, when the configuration is static. That means when we know all the jobs that the system can ever run at the beginning. However, real operating systems, jobs come and go, right? So we jobs come at different random times. So shortest job first, although theoretically this is best, but we cannot use it because we don't know the future. It's kind of impractical to use on real systems.
So when you say that SJF is optimal, do you just mean that it has the lowest turnaround time?
Yes.
Okay.
Yeah.
So it's not concerned with the other statistics we talked about?
No. It has nothing to do with response time. No.
Okay.
So if we want to optimize on turnaround time, and given that we have all the requirements of SJF, then yeah, SJF is the best thing that we can use.
Okay. Thank you.
So another variation of SJF is SRTCF. So here basically this is a preemptive version of SJF. Okay, so SJF is non-preemptive uh, because we never stop or like pause the running process, right? We never snatch the CPU away. Whereas SRTF is a preemptive version of SJF where we make a scheduling decision at real time whenever whenever a process arrives. So whenever a process arrives, for instance, when C arrives, C is the only job. So we just keep on running C. So when A arrives, we know that A has the shortest time to complete. So we run A. Then once A finishes, we start with C because C is the only job at that point. And when the B arrives later, we know that remaining time for C is actually greater than the time of B. So we start with B. That way, uh, we always make sure that CPU is always running the job which has the shortest remaining time. Okay. I mean, obvious disadvantages of SRTCF is it can cause starvation, because now you can imagine that if there is a long running process, it may never finish. Because imagine if there is a long running process and there are continuous smaller jobs that are arriving. So even though the long running job is running for like 2x of its time, it may never finish because CPU is always busy running the shortest job. So to summarize, we know that FIFO has the highest throughput because it always does the work needed by the process, right? There is almost no overhead whatsoever. Okay. And round robin, it has good response time. Of course, it depends on the quantum timer value, and it has decent turnaround time, and it's very fair. And shortest job first, we know that given all the jobs are static, given all the jobs arrive at the same time, and we know the completion time of each job, then shortest job first scheduling has the minimum turnaround time. Okay. So let's look at like real operating system. Okay. So Linux kernel, there is no one scheduler that is used. Okay. Although I think now Linux kernel uses priority scheduling, which we'll be looking into in the next class, like what is priority scheduling. That's why, like, if you have worked with Ubuntu or like Linux based system, you might have used this nice command to increase the priority of a process, right? Like if you remember, most of the time, like in usually on servers, people use this command called nice to increase the priority of a process so that it gets scheduled more often. So, but like priority based scheduling is the default scheduling policy in most of the flavors of Linux kernel. However, it varies with the different flavors, right? For instance, on Ubuntu, it could be priority, whereas on Fedora, it could be different. It could be a minor variation of priority scheduling. But most of the Linux kernel flavors, they use one variant, at least a small variant of priority based scheduling. Okay. And by the way, you can actually customize the scheduling policy of Linux kernel. So there is a system call called set scheduler, where you can set the scheduling, like current scheduling policy on your system. So you can actually explore this system call and I'll try to post few examples. I mean, I could demo this thing now, because it might slow down my system, because the Zoom call might end, because if I set the scheduling policy to FIFO, then the Zoom might never get to run. So I'm not doing that, but you can experiment with this set scheduler on any of your VM and see what happens. Okay. And yeah, let's do a quick review. Okay. So which scheduler is good for, like, for instance, mobile devices? Of the schedulers that we have just seen now, like 4 schedulers, which do you think, like if you have given only 4 of these choices, which one you would pick and why, of course? Yeah. Okay, let's try to go through each of our scheduling policy, right? So is FIFO a good scheduling policy for mobile devices?
Yeah, because you're only ever running one thing at a time.
Oh, okay, very good. But FIFO always runs first come first serve, right? So if one application is running, let's say you want to like you want to open up another application, then it may be you need to wait till the current application finishes. Do you really think that's a good scheduling policy? Because when we are using a phone, right, we want, if we run something and if it is just stuck running, uh, we don't want that, right? We usually want, we should have an ability to just run arbitrary apps. Like we don't want like first in first out. So what about shortest job first? Can we use shortest job first on mobile devices? Of course not, right? Because we don't know how much time we will be spending on each app. So if I'm playing a game on my mobile phone, I may be playing for 15 minutes compared to if I'm on Twitter, I may be spending 5 minutes. So the time that I use for each app varies with the app and my mood. So shortest job first, no, I cannot use, I mean, that's not the ideal scheduling policy. So from the policies that we have seen, it seems to be like round robin seems to be the best policy for mobile devices, right? Because it provides responsiveness. That's exactly what we want on our phone. Like when we open an app, when we click an app, we want the app to respond quickly. We don't want to wait, like to stare at our phone screen for the app to open up, right? We want the app to be snappy, that it just comes up. So yeah, from the four scheduling policies that we have seen, uh, round robin seems to be a better fit for mobile devices. Okay, what about servers? Let's say you have a server where you just submit jobs. Which scheduling policy do you think is good for servers? Anyone? There is a hint. This is actually easy.
Shortest first. Also, a lot of people are putting their answers in the chat.
Oh, sorry. I'm I'm sorry. I very sorry. I just there is some problem with the Zoom, so my chat window goes all the way above, so I cannot see.
Yeah, but the answer that most people put was shortest process first.
Oh wow. I just, yeah, that's true exactly. So we want shortest job first. Uh, yeah, given that we know the uh, running time. However, like if we don't know the running time, then we can use FIFO as well. So good. Yeah, that's uh, that's very nice. And by the way, quiz 2 is now online, so you can access quiz 2 from Brightspace. So it covers concurrency, deadlock, and resource allocation graph, and some analytical problems with resource allocation graph. Okay, I so wish today was in person, because I plan to show dining philosopher's problem and see how we can change our solution and prevent deadlock by evading each of the deadlock conditions. but I had to change my lecture because of the unfortunate snowstorm and make it online friendly. Uh, I think we are done. So if you guys have any questions, please, I'm still opening my chat window. Okay, hey, now I can see. Okay, now I can see. Okay, as if you have any questions, please ping on the chat, or you can just ask to. So I'll try to post quizzes like once in a week, or maybe like two quizzes for every 3 weeks. Okay. And before midterm, like 1 week before the midterm, I'll be giving some practice midterm question papers, like so that you can get an idea of kind of questions and get yourself like equipped with the knowledge that you may need for the midterm.
Sorry. Are the quizzes for a grade, and how similar are they to the exams?
So the style will be same. Okay, in the sense like there will be multiple answers. There'll be select the correct like select which one of the statements is true. The style of the questions will be same. And with respect to similarity, you can imagine that like 40% of it will be concept based. Okay, so where you need to know certain concept to answer. And there will be like 20 to 30% analytical based, where you need to do some reasoning to answer the question, where you need to apply the concepts. So in short, yeah, it will have similar flavor, but I cannot generalize it because quiz has only like 8 to 10 questions, right? So maybe the practice midterm papers might give you more idea.
Okay. And are the quizzes graded?
No,
Okay.
but I strongly suggest you to take it, like even though they are not graded, it's just
Yeah,
for
yeah,
you
of
to understand. Yeah.
course.
Okay, guys. Yeah, I'll be here for 5 more minutes. So if you have any questions, please feel free, or we are done for today.